So what can we do in other cases? So how can we interpret, for example, the results of naive Bayes or a support vector machine? There's really no clear answer. There are different proposed techniques, and we're going to go through each one of them right now. In contrast to random forest and neural networks, which are the exceptions actually, most machine learning algorithms do not embed feature selection or any kind of interpretation capabilities. This is why we have this niche of interpretable machine learning, and this is why people are coming to come up with model agnostic techniques to interpret machine learning models. And what I mean by model agnostic techniques, I refer to techniques that can work for any kind of model. All right, it doesn't have to be a random forest or a neural network. It could be anything. It could be a support vector machine, naive Bayes. It could even be, let's say, evoking a sample of 10 different classifiers. So we're going to see a few of these techniques, and we're going to start with partial dependency plots. So partial dependency plots is basically a pretty simple but effective idea. So let's say that we have this example here taken from scikit-learn, which refers to the California dataset. It's a dataset where the objective is to predict the value of properties in California. Let's say that you want to understand how the house age affects the response variable. So how you do that? Well, you just marginalize, basically you average all the variables across all instances for its value of house age. So that's pretty simple. In this case, you see that house age ranges from, let's say, 9 to 50, 51 or so, and you sort the values in increasing order, and you start at 9. And then you simply average all the variables, and you get a prediction, and then you average all the predictions, and you see that, in this case, for example, the price is close to 0.1. Obviously, these features, their response is normalized. That's why we get this kind of values. And then you repeat this for its value of house age, and you can see very nicely that, there's a positive relationship between house age and the price, in some cases, but it flattens out a bit. However, this technique is obviously not perfect, right? So in machine learning, quite often we have nonlinear spaces, we have lots of nonlinear interactions. With this technique, with partial dependency plots, we're not going to be able to understand the case where clusters of our instances might behave in a different way for the same variable. Why? Because what we're doing here is we're marginalizing across all variables, but also across all instances. So we take in, let's say, the value house age equals 30, and we get the predictions from all instances, and then we average them out, and we come up with a single number, let's say 0.3 or so. However, there might be a case where half of our instances might have a higher value, let's say, 0.6, and half of the instances might have value 0, and, when averaged, we end up with 0.3, but in reality, we don't have a single cluster where most of the instances are 0.3, but rather we have two distinct clusters. And this is why we have individual conditional expectation plots, which is basically a more granular version of partial dependency plots. In this graph, it's an example from the original paper, which is about individual conditional expectation plots, which is copied from arXiv. And in the middle here, you have a partial dependency plot, right? And you see basically that you have a variable, and test approaches 0, then something happens, and then, the values are a bit higher. It looks like you have a bit of a nonlinear effect, but, this variable doesn't look very interesting when you only check the partial dependency plot. Again, in case you didn't realize, the partial dependency plot is represented by the line in the middle, the thick black line with a yellow outline. When you check the individual conditional expectation plots, which are created by marginalizing across all variables, but creating a different plot per instance, you can see that you actually have distinct clusters. So you have some instances that are in the top of the range of the response variable, some in the middle and some in the bottom. Around 0, they all collapse to the same value. Then they separate again. And the behavior changes slightly between the different clusters, as you can also witness. So this is where a partial dependency plot does not offer much information. However, the individual conditional expectation plots makes us realize that there's something very interesting going on in this variable. Another method is the method of global surrogate models. So this is not a plotting method. This is a very interesting heuristic where we're just using a simpler model to explain a more complicated one. So let's say you have a neural network or an ensemble or XGBoost, etc. So you take the output of the model we want to study, and basically you map the input features to the output of the model, and you use in the middle a simple interpretable machine learning model, which is usually a decision tree, but a simple decision tree. I'm not talking about random forest or anything like that. A decision tree where you determine, for example, the depth to be not more than 7 or some arbitrary value. And you get a model back which is very easy to read for a human and can help them understand how the model actually reaches the decisions. It's like a simplified version of the original model. This method is very easy to use but has some misuse. First and foremost, you know that you're not going to capture all of the variance captured by the original model. So if on one hand you have, let's say, complicated ensemble and then you try to approximate this using a simple decision tree, well, you know in advance that you can't do that well. You just can't. However, the benefit of this method is that it's just basically very easy to use. Any data scientist can code this in a matter of minutes. However, a more interesting technique following the same principles of surrogate models is a technique called LIME. LIME stands for Local Interpretable Model Agnostic Explanation. So this technique works in a very smart way. First of all, this technique is used to explain individual instances, okay? It's not used to explain what's happening, in general in the algorithm. We care about, an instance. So what we're doing is we basically permute the data set to get lots of different predictions, and then we weight these predictions according to how close they are to our instance of interest. So we get this new dataset, basically this permute dataset, which is also weighted, and then we feed this into some easy to understand models such as ElasticNet or Lasso, etc. And this can help us understand which parts of the feature space are important. So here's an example to show you how this works a bit better, because LIME can seem a bit complicated initially when in reality it's not. So let's say that we want to understand how a classifier classifies an image. Okay, so on the left hand side you have the original image, that of a frog. So the first thing to do is to basically break this image like randomly in different components, like a puzzle. We don't care about the individual pixels, we care about areas of this image. Okay, we know that the algorithm is going to be using whole areas in order to create the classification and not just individual pixels. So we've done this, we segmented the image in different parts. Then what we're doing is we start permuting, basically create new datasets from original datasets, and we ask our classifier to come up with new predictions. So we provide the classifier with an image of the head of the frog, and we ask it to predict whether this object is a frog or not, and we get the probability 0.85, right? Then we provide another image where the head is missing and the body is missing, but some other parts are there, and the probability is practically 0. And then we have another image where we have the body and we have the head, but something else might be missing, and we get a probability of 0.52. Okay, so this gives us basically a data set where we know what the permuted input was like and what the algorithm predicted. And then we run locally weighted regression, again, as I mentioned, using some method like ElasticNet. And this gives us the most important feature for this type of classifier, for classifying frog, this particular area, which represents the head of the frog. So as you see, it's a few different steps we follow in this method. However, what we're essentially doing is just permuting the dataset, getting predictions of a classifier, and then running regression to figure out which of the input features seem to be most useful for predicting a given instance.